In the chapter Central Forces, till now we have discussed so many important concepts. First of all, you have seen the meaning of central force and its different properties. We have discussed its different properties in very detail. And after that, we have obtained the equation, general equation of orbit in differential form, and we have also seen the solution of that very equation, particularly in the case of attractive central force field which obeys the inverse square law. You know that the gravitational force is a very important example of central force which is attractive and also obeys inverse square law. Now we are going to see the most important concept of this chapter, and this important concept is related to actually laws of planetary motion. Definitely you have heard that Kepler, one of the pioneer of physics, has proposed three laws of planetary motion. Actually, the motion of planets has been a subject of much interest for astronomers from very early times, and these Kepler's law, you know, have been initiated purely on the basis of observations taken from the motion of the planets. Actually, these are very simple laws and accurate, and it gives actually the accurate description of planetary motion. But one thing is very remarkable, that these laws do not offer any explanation. So you can say that we can obtain so many informations, so many useful informations regarding the planetary motion from three laws of Kepler. So in this lecture, our aim is only to know what are these Kepler's laws of planetary motion. And after that, we will see the deduction or derivation, which is also very important for your examination, particularly the examination of BSc and MSc. And after that, we will see the applications of these Kepler's laws of planetary motion, which will be very important for competitive examinations. Okay. So now let us start to know what are the three laws of planetary motion proposed by the famous scientist Kepler. The first law is known as the law of orbit, because this law deals with the orbit or the trajectory along which a planet moves. You know, there are 8 planets and all planets revolve around the sun. But what will be the trajectory or the orbit followed by the planet? This first law of Kepler deals with. In fact, according to Kepler's first law, every planet moves in an elliptical orbit. It means the orbit of each and every planet is an ellipse around the sun. And you know that an ellipse has 2 foci. As in this figure you can see, this F1 and F2 are the focus of an ellipse. According to Kepler law, every planet moves along this elliptical orbit, and the sun remains at one of its foci. As I have shown in this figure, that the sun is situated at the focus F1, but it may be at F2. So according to first law, all planets revolve in elliptical orbit having the sun at one of the foci of the ellipse. Okay. Now I have shown here actually the semi-major and semi-minor axis too, but that will be required after some time. You can see A is the semi-major axis of this axis and B is its semi-minor axis. Okay. And here I have shown the planet, and this planet is revolving in this elliptical orbit. Okay. This is actually the first law. We will see the proof of this first law in the second lecture. Okay. Now, the second law of Kepler is also known as the law of area, or you can also say that this is law of areal velocity. In fact, this law of area states that the radius vector, you can see with respect to the sun, this is actually the radius vector of our planet. This vector r is the radius vector of this planet. Okay. This law says that this radius vector or the position vector of the planet with respect to the sun sweeps out equal area in equal time interval. Equal area in equal time interval. Or in other words, you can also say that the areal velocity of the radius vector is constant. What is this areal velocity, how it is defined, we will see here. But first of all, see this figure. In this figure, I have shown that at this position S, which is focus of this ellipse, sun is situated, and at any time t, a planet is at this position P. And after a very short interval of time dt, this planet moves to the new position P prime. Okay. And when the planet was at P, its radius vector with respect to the sun was r, you can see in this figure. And so, when the planet moves from P to P prime in time dt, you can see that this radius vector sweeps out an area which is equal to SPP dash. That is area of the figure SPP dash. This is area swept out by the radius vector in time dt. So, area of figure SPP prime equal to area swept out by the radius vector r, radius vector r in time dt, okay. If you consider that this area is very small, then we can treat this area as an area vector. So let us say this area is equal to dA, and if you treat it like a vector, then this will be vector dA. So in time dt, this area dA has been swept out by the planet. So in unit time, what will be the area swept out? Velocity, areal velocity means area swept out by the radius vector in unit time. So this dA by dt, this is actually the areal velocity VA of the radius vector. And according to this second law, this dA by dt, which is equal to VA, this will be actually constant. Okay, this will be constant. And as in a statement, it has been also said that the planet, that the radius vector of the planet with respect to the sun sweeps out equal area in equal time interval. You can see this second figure. I have considered here that a planet is at a position P at, let's say, at any time T1, okay, and it is at position P dash, let us say, at time T2. So in this time interval T2 minus T1, in this time interval T2 minus T1, the area swept out by the radius vector r, that is SP, will be what? In this time, in this interval, the area swept out will be equal to area of the figure SPP dashed. So area of SPP dashed, this will be equal to area SQQ dashed, but only when time taken by the planet in moving from Q to Q dash is same as that the time taken by the planet in moving from P to P dash. Let us consider that at point Q, the planet is at a time t3, and at Q dash it is at a time t4. Let us say. Then the time interval in which the planet moves from Q to Q dash will be what? That will be equal to t4 minus t3. Okay? Then, according to this second law, if this t4 minus t3, if t4 minus t3 is equal to t2 minus t1, if this condition holds, then this condition will also hold. It means when time interval is same, then the area swept out by the radius vector will be same. So you can say that if a planet takes equal time in moving from P to P dash and Q to Q dash, then the area of SP P dash figure and SQ Q dash figure will be equal. Okay? So this second law is stated in two forms. The one of the forms is simple, which says that the areal velocity of the radius vector is constant. Okay, I think you have understand what is the law of area. Okay. Now, the third law of Kepler regarding the planetary motion is also known as the harmonic law. This is called harmonic law or law of period. Okay. According to this harmonic law, the time taken by any planet revolving once round a trip along its elliptic orbit is called its period of revolution. Let us say, if a planet starts to move from this point, let us say P0, and it moves along the elliptical orbit and returns back to this point P0, then one revolution is completed. And in this one revolution, if the planet takes time capital T, then this capital T is actually called period of revolution of the planet. Actually, this harmonic law says that the square of the period of revolution of a planet is directly proportional to the cube of the semi-major of its elliptic orbit. Mathematically, so you can say if T is the period of revolution and A is the semi-major axis, then according to this law, this T square is proportional to A cube. And when we will replace this sign of proportionality, there must be a constant here. So T square will be equal to a constant times A cube. In other words, you can say that T square over A cube will be equal to constant. Okay. So now if you consider two planets revolving along their orbits, let us say the semi-major axis of the first orbit is, let us say, A1, and that of the second orbit is, let us say, A2. Okay. And the period of revolution of the first planet revolving along this orbit having the semi-major axis A1 is, let us say, T1, and that of the second is T2. Then, according to this equation, the ratio of T square and AQ is since constant. So you can say that T1 square over A1 cube is equal to T2 square over A2 cube. And in other words, you can say that T1 over T2 whole square is equal to A1 over A2 whole cube. Actually, this law is very useful in comparing the period of revolution of two different planets. If you have an idea or if you have given a data of the semi-major axis of the orbits of two planets, you can easily compare the period of revolution by this third law of Kepler of the two planets. Okay. So I hope you have understand what are the three laws. These are very basic and fundamental law, very simple law proposed by Kepler. Okay. As I have told you that in the next lecture we will see the derivation or deduction of these laws. Okay. But before that, in this lecture, I am going to solve a very important problem which will be very useful for your examination. And for solving that very problem, you have to remember the previous lecture which I have dealt in the previous videos, and let us see what is that very important problem here. I have mentioned the problem here that you can see the problem says that the eccentricity of Earth's orbit is 0.0167. Okay. Then we have to calculate the ratio of the maximum and minimum speed of the Earth in its orbit. You know, Earth is a planet, okay? And as it is a planet and it is revolving around the sun, according to Kepler's first law, definitely its orbit will be elliptical, okay? And you know, the eccentricity E of an ellipse is less than 1. So you can see in the data of this problem that eccentricity of Earth's orbit has been given 0.0167, which is less than 1. Okay, this must be so. Okay. Now, in this problem, we have to find the ratio of the maximum and the minimum speed of the Earth. Okay. Since the motion is along an elliptical orbit under the gravitational pull of the Earth, and since orbit is elliptical, so distance of the planet, that is the Earth, from the sun regularly or continuously changes. And you know, gravitational force is distance dependent. So if distance between sun and Earth is changing, definitely the magnitude of the force acting on the Earth is also changing. Okay. And when the force acting on the Earth due to the sun changes in its magnitude, definitely the speed of the Earth will change. So at different points on the orbit, the Earth will have different speed. Let us consider at any moment our Earth is at this position P. This is the position of Earth. And sun is here, which I have marked by the letter S. And when the planet, that is Earth, is at P, let us say its speed is V. Okay. Now this Earth revolves, and when it is at position P1, see the figure, then I have assumed that its distance from the sun is R1. And when it is at P2, see this figure, then its distance from the sun is R2. I have marked here. You can see the figure. Actually, when the Earth is at P1, its distance R from the sun is minimum. And when it is at P2, its distance from the sun is maximum. When a planet is at the minimum distance from the sun, that apsidal distance is actually, or that position of the planet is called perihelion position. So when the Earth will be at P1, it is at its perihelion position. Okay. And when it is at P2, it is farthest, it is at the largest distance from the sun, and this position of the sun is called aphelion position. Okay. I think you have an idea of this. And you know, gravitational force F is an inverse square law force. It varies inversely with the square of the distance. So when the Earth will be at P1, that is at its perihelion position, the gravitational force acting on it due to the sun will be highest. And when it is at P2, this force will be minimum, that is at its lowest value. And so you can guess, when the force acting on the planet will be largest, then its speed will be actually largest. So if you consider that a speed of the Earth at this perihelion position is V1, then V1 will be actually the maximum speed of the Earth. Okay. And when it is at its aphelion position P2, then its speed I have assumed here V2, this will be actually the minimum speed. Okay. So along the whole trajectory, when the Earth is closest to the Sun, that is at its perihelion position, its speed will be maximum, and when it is farthest from the Sun, that is the Earth is at its aphelion position, then its speed V2 will be minimum. And in this problem, we have to find what will be the ratio of this V1 and V2. V1 is the maximum speed and V2 is the minimum speed. So what will be V1 over V2? We have to find it. And in the only data given in this problem is the eccentricity of this orbit. So think how we can solve this problem. Okay. Actually, starting from the equation of orbit in polar form, you can easily solve this problem. Okay. Let us see, I have assumed that the Earth at any moment is at this position P when its radius vector with respect to the Sun is r, and making an angle theta with this major axis. Okay. So you know, in this condition, the equation of the orbit of the planet in polar form is given by this equation. You have studied this equation in the previous lecture. So remember the facts of the previous lecture, then you will easily understand each and everything. If you have not gone through the previous lecture, you must watch my previous video on the solution of equation of trajectory under of a particle moving under a central force field obeying inverse square law. I have actually published already this video, so you can watch that. When we will watch that video, you will find that the equation of orbit is given by L over R equal to 1 plus E cos theta. In this equation, L is a constant which is also called semi-latus rectum. Okay, and E is the eccentricity of the orbit. Okay, now you can see that at when the planet Earth will be at different position, this theta will vary. Okay, and you can see when theta is equal to 0, it means the planet is at this position P2. Planet is at this position P2. In that condition, cos theta will be equal to 1 because cos 0 is 1, and you know 1 is the maximum value of cos theta. So 1 plus E cos theta will be maximum. It means L over R, that will be maximum. If L over R is maximum and L is a constant, it means 1 by R is maximum. 1 by R. I am not saying R. I am saying 1 by R is maximum. And you know, if 1 by R is maximum, it means R is minimum. Are you getting the things or not? If 1 by R is maximum, that means R is minimum. And I have assumed in this figure that minimum value of R, that is minimum distance of the Earth from the Sun, is R1. So R minimum we have assumed equal to R1, and this is the perihelion position of the Earth. So if you will put cos theta equal to 1 or theta equal to 0 in this equation 1, you will get the minimum value of R, and that is equal to R1. So you can write L over R1 equal to 1 plus E. Why E? Because cos theta is 1. So you can say that R1 is equal to L divided by 1 plus E. L divided by 1 plus E. Okay. Now, similarly, you can see that when this theta will be equal to pi or 180 degree, theta will be equal to pi or 180 degree, then cos theta will be what? You know, cos theta will be equal to -1, and -1 you know is the minimum value of cos theta. And if cos theta is minimum, then 1 plus e cos theta will be minimum. So you can say that L over R is minimum. Again, remember, L is a constant. So L over R minimum means 1 by R minimum. And if 1 by R is minimum, that means R is maximum. R is maximum. And in that figure, you have seen that I have assumed that this R maximum is equal to R2. And this is actually the aphelion position of the Earth. Okay. So in that equation 1, if you will put R equal to R2, then cos theta will be equal to -1. So that equation becomes L over R2 equal to 1 minus E. And therefore, R2 is equal to L over 1 minus E. Okay. So we have actually calculated the values of the minimum distance of the Earth and the maximum distance of the Earth. So from these two equations, we can easily see what will be the ratio of these two distances, that is maximum distance and minimum distance. So you can see R2 over R1 will be what? Let us calculate. R2, you know this is L over 1 minus E, and R1 is what? This is L over 1 plus E. Okay. L and L will cancel out, and this will be simply 1 plus E over 1 minus E. Okay. Now see, while dealing with the motion under a central force field, I have discussed in very detail that whenever a particle or a body moves under a central force field, the angular momentum of the particle remains conserved, remains constant. Okay. Here, this Earth is moving in the central force field of the Sun. So definitely, the angular momentum of our Earth will remain conserved. Okay. So if its angular momentum remains conserved, what does it mean? It means angular momentum of the Earth when it is at its perihelion position, that is when it is at P1, and when it is at P2 will be equal. So from the conservation of angular momentum, we can write very easily. So as angular momentum remains conserved in central force field. Therefore, at position P1, what will be the angular momentum of the Earth? You know, this will be m v1 r1. Okay. And at position P2, this will be m v2 r2. Okay. M is mass of the Earth, and so it has been taken same in both sides. And from here, you can see what will be R2 divided by R1. R2 divided by R1. This will be simply V1 over V2. V1 over V2. And you can also examine this equation as here R2 is maximum. R2 is maximum and R1 is minimum. It means minimum distance from the Sun. So this implies that V1 will be maximum. Okay. And this implies V2 will be minimum. And what's the reason behind this? I have already told you that actually at the perihelion position, the magnitude of the gravitational force acting on the Earth due to the Sun is maximum. So the speed is maximum. Okay. So if you want to find the ratio of the maximum and minimum speed of the earth during its motion around the sun, then you have to find the ratio of R2 and R1. But according to equation 4, this ratio of R2 and R1 is 1 plus E by 1 minus E. So from equation 4 and 5, we can easily say that V1 over V2 will be equal to what? This is 1 plus E over 1 minus E. And see your problem. In our problem, the eccentricity E of the Earth's orbit is given. This is 0.0167. So when you will substitute this value of E in this equation, you will find the required ratio. So this is 1 plus 0. What? 0.167 and over 1 minus 0.0167. And when you will simplify this ratio, you will get simply 1.03. So you can say that the ratio of the maximum and the minimum velocity or speed of the earth, this is actually V max and this is V minimum. Okay, this will be equal to 1.03. This is the answer of this problem. Okay, and from this result, you can very easily find a very important result. Since you have seen that this V max, which is V1 here, over V minimum, in terms of eccentricity, this is equal to this much. You can see this is 1 plus E over 1 minus E. Doing a very simple algebra, you can see what will be the result. A very important result we can derive. In fact, if we will subtract 1 from both sides, let us see here, V max over V minimum, minus 1. What will be this? This will be 1 plus E over 1 minus E minus 1. And this will be V max minus V minimum over V minimum. Okay, I have taken LCM simply, and that will be what? This is 1 plus E minus 1 plus E and over 1 minus E. See, this is simply V max minus V minimum over V minimum, and what will be this? Here this 1 and 1 will cancel out, and this is 2E over 1 minus E. Okay. Now see, I am just following the forward steps here. You can see. Now let us add 1 in both sides in this expression. So you can see that this V max over V minimum plus 1. What will be this? This will be simply 1 plus E over 1 minus E plus 1. And doing the same algebra, you can see this is V max plus V minimum over V minimum. What will be this? This is 1 plus E plus 1 minus E and divided by 1 minus E. And here this E and E will cancel out. So this is simply 2 over 1 minus E. Say this is your equation A1 and this is equation A2. Let us say. Okay. Now, if we will divide this equation A2 by this equation A1, what will be our result? Since in denominator in LHS there is V minimum, that will cancel out, and so you can see that this V max plus V minimum over V max minus V minimum will be what? This will be 2 over 1 minus E over 2E over 1 minus E. 2E over 1 minus E. And what will be this result? You can see 1 minus E will cancel out 2 over 2E. This will be simply equal to 1 over E. Okay? And therefore you can see that this V max plus V minimum over V max minus V minimum, this is equal to 1 over E. So this is also a very important result, and in several examinations such type of results is asked to prove. I think you have understand the solution of this problem very easily, and as I have told you, in the next lecture we will see the proof or the deduction of these three laws of Kepler, and then we will see the applications of these laws. Okay.